In this clip we will take a look at hash tables. Hash tables are typically implemented in two flavors. The first flavor is a container that stores the values that are added directly, just like arrays and linked lists. This container is often called a set or a hash set. The other flavor is a container that maps a set of keys to a set of values. This is typically referred to as a map or a dictionary. Here are the corresponding data types in C#, Java, Python, and C++ respectively. You might remember these two code snippets from the introductory module. It's two implementations of a method that reads a bunch of lines from a log file, extracts the visitor's IP address, and stores all unique IP addresses in a container. In the example, I used a dynamic array or a list type in the C# implementation to the right, and an NS mutable set in the Swift implementation to the left. The NS mutable set type is implementing a hash table, and in a moment I will explain what exactly that is. But remember that we saw that despite having much less capable hardware, an iPhone was able to beat a relatively powerful laptop just because of one single difference in the implementation: the use of a hash table instead of a dynamic array. In the module about dynamic arrays, we saw that finding an element in a list potentially requires all elements in the list to be scanned, and thus results in a complexity of big O of n if there are n elements in the list. And finding an element in a C# list is done with the .contains method. Now, if we not only need to search the list once, but need to do it for each of the elements we add to it, then the complexity of the entire operation is in the order of big O of n squared. And that's a performance killer. To illustrate the point, I have run the count unique IPs method for a large number of different log file sizes and measured its completion time. The execution time increased with a factor of around 4 when increasing the number of elements with a factor of 2 from 30,000 to 60,000 elements, but increasing the number of elements with a factor of 10 from 10,000 elements to 100,000 elements increased the execution time with a factor of around 100. There must be a better alternative for this kind of job, and we have already seen in the intro that there is. The alternative is called hash tables, but in order to explain hash tables, I need to introduce you to hash functions. A hash function is basically a mathematical function that takes its input values from a large and in principle unbounded domain and maps them to a smaller fixed size domain. Good hash functions have the nice property that whenever values are different in the original domain, there are a high probability that they will also be different in the target domain. Of course, since the target domain is smaller and of fixed size, we would end up with collisions if we were to map each and every possible value from the large and perhaps unbounded input domain. But in practice, in most situations, the fraction of actually used input values out of the whole domain is small, and therefore there will, in practice, typically be room enough in the target domain to map all of the values without collisions. One category of hash functions is functions that map from the domain of all possible strings in the world, which is a huge domain, to a domain of strings with fixed length. An example of such a hash function is the MD5 sum, which here maps the string Pluralsight to a 32-character string. In fact, that string is a 128-bit number, but it is typically written in hexadecimal. But imagine how large a 128-bit number is, and how small probability there is for two randomly chosen 128-bit numbers to be the same. That is sort of the probability for two hash functions to collide. Here I have used Pluralsight with a capital P as input, and as you can see, the output is completely different despite the small variation in input. Another category of hash functions maps to 32-bit integers. In C# we can call the getHashCode on an object and in this example I have called it on the string plural side. Again we see that just changing the small p with a capital P changes the output completely. This was 4 examples of hash functions with strings as input, but hash functions can take any bit sequence as input. And with that, we are ready to introduce hash tables. Like dynamic arrays, hash tables uses an array of fixed size as internal backend storage. Here is an array of size 8. Each position in the hash table is referred to as a bucket. In order to insert an element, say 25, a hash function is evaluated on that element, and its return value specifies the desired position of the element. In this case, the element should go to position 3, which is here, when counting from 0. Let's insert another element, say 23. In this case, the hash function returned 6, but as you can see, this bucket is already occupied. Now we have a collision, and there are numerous strategies for dealing with collisions with different pros and cons. If you are interested, you can visit the article about hash tables on Wikipedia and look up under collision resolution. The strategy I will explain here is the use of overflow chains. That is, in case of a collision, all elements that are sent to the same bucket are stored in a linked list from that bucket. In our example from before, the element 23 is added after 17. For practical reasons, hash tables require the contents to be unique, so depending on implementation, adding the element 23 again would either result in an error being thrown, or that the second 23 is ignored so that only one representative is stored. There are, however, variants that support duplicate keys, but in most practical situations where a hash table is relevant, the uniqueness property comes in handy. Let's, for the sake of illustration, add some more overflow elements. But remember that this is supposed to happen really rarely. When the hash table is sufficiently full, a larger array is allocated and all elements from the old array are copied to the new array, but with use of a hash function that covers the whole new array. This reorganization step is also referred to as rehashing. By the way, notice that the order in which the elements are put in the new array is different from that of the old array. But that's okay. Hash tables do not guarantee any ordering. They can store and look up individual elements, but they do not support element sequences. Let's do some complexity analysis of the common methods of hash tables. Inserting an element, say 25, was done by computing the hash function of the value and storing the element in the position specified by the hash function. This can either be in an empty bucket or at the end of an overflow chain in case of a collision. In either case, computing the hash function is independent on the number of elements in the hash table. So we can consider the used number of instructions to compute the hash function as constant. Storing the element is also done independently on the number of elements, and thus that operation is also constant. So adding an element to the hash table is done in constant or big O of one time. However, occasionally the values need to be rehashed into a larger array, and if there are n elements in the table, that will take big O of n time. When we discussed the reallocation that happens in dynamic arrays, we also discussed the complexity of such a reorganization. One of the key arguments was that even though the reallocation will be performed for more and more elements as the hash table grows, it will also be done more and more rarely. And with a little bit of math, it can be seen that even though the worst case complexity is big O of n at these rehashing peaks, the amortized complexity when adding n elements instead of just one stays at big O of one time per element. By the way, there is one little detail more about the insertion complexity. If an element to be inserted lands on an overflow chain, all elements in that chain needs to be scanned for duplicates, because hash tables in general require element uniqueness, and that can, in principle, be a big O of n operation. However, in practice, long overflow chains are extremely rare, and if they exist, they may be a witness of a poor hash function. Finding an element in the general case is a matter of computing its hash value and looking up in the array at the position specified by the hash value. And that's a constant time operation. Notice that for arrays and linked lists, this was a big O of n operation, so this is much faster. If we are very unlucky, however, the element to be searched for is hidden within a long overflow chain, and in that situation, the whole chain may need to be searched. There can be at most n elements in that chain, so the worst case scenario, even if it's very unlikely, is big O of n. Removing an element is, just like for the other operations, done by computing the hash of the element and emptying the bucket for the position specified by the hash. That's a fast big O of 1 operation. If we are unlucky that the element sits in an overflow chain, we need to scan the chain in order to find the element, and this is a big O of n operation. So, in general, a hash table provides constant time operations for add, find, and remove. There is technically a risk of a linear time worst case scenario, but in practice, the far most use cases should just rely on the constant time property. In the hash tables seen so far, we have stored plain values. There is a variant, however, that is very frequently used. And that variant is often referred to as a dictionary or a map. Instead of storing plain values, tuples on the form key, value are stored so that the storage position of the tuple is determined by evaluating the hash function of the key. The value part can be considered as the interesting payload. If we were to construct a lookup table that maps user IDs to usernames, one entry could look like this, mapping the user ID 2 to the username James. Here 2 is the key, while James is the value. Similarly, the key or user ID 16 maps to Claire, and so on and so forth. With the constant time characteristics of hash tables, we can quickly look up the name of a certain user ID, and this makes hash tables ideal data structures for caches. Fast insertion, fast lookup, and fast deletion. And we have no interest in receiving elements in the same order they were added, which is one thing that arrays can offer that hash tables can't. Speaking about caches, we use a list type as cache in our investment analyzer, but we have seen how finding an element takes big O of n time. Let's use a hash table or a dictionary instead. Let me head over to Visual Studio and adjust the code. So here we are back at the investment analyzer, and instead of using a list as our stock to rating cache, I would like to use a dictionary instead. So I write dictionary, and the dictionary would take a key type, which is a string because the stock ID is a string, and the rating is an integer, so the value type is int. And let me get rid of this. And similarly over here, I will just make a new instance of a dictionary of the same type. New dictionary of a string and an integer. Okay, there is no reason to keep this rating cache element around anymore, so I'll delete that. And down in the code where we are accessing the cache, I'll delete this line and just ask if our stock to rating contains a key with the value of our query .stock ID. If that's the case, I will use the value associated with that key. So I write stock to rating and just query for that stock ID again. Here we are. So the last thing to do is to go down here and adjust the code where we are adding a new element to the cache. The dictionary.add method takes a key and a value. So the key is our query .stock ID and the value is our rating. So that's it. Let me try to run the code to see how fast it goes now. 0.32 seconds plus the 0.23 seconds above. That's fast. Let's take a look at the evolvement in the execution times. We went from 117 seconds to 110 seconds, down to 6.48 seconds, and now we are down at 0.55 seconds. That's a 214 times execution speed up compared to the first original execution time. And all that came for free, just by knowing and using the right data types for the job.